The previous steps, color transform and decorrelation transform, only rearrange the data and are reversible, thus they are lossless. Instead of removing redundancies, we now want to remove all the irrelevant information. We do that by decreasing the accuracy of the coefficients we obtained from the decorrelation transform. Therefore, we assign a range of those real-valued coefficients to an integer value, which then represents all the values in that range. That process is called quantization. Of course, this process is not reversible, because more than one values are mapped to the same integer. To achieve the smallest distortion, the dequantization has to assign each of the integers a value that represents the original range the best. As stated before, the purpose of quantization is to eliminate all the information that a viewer can't perceive or is able to tolerate. The diagram you see here shows the principle of the quantization system. Each value that happens to fall in the range between the thresholds ti-1 and ti is assigned to the index I. During dequantization, that index I is mapped to the reconstruction value xi hat. Therefore, the index I represents the entire cell or bucket of the width delta I. On the one hand, an increase of the number of available cells increases the quality, but on the other hand also results in a rate gain because more different values have to be encoded. Let me show you an example. Here the sequence of DCT coefficients from the previous example is given. We are now going to quantize those values with a quantizer with constant cell width of delta equals 2. The computation rule you can see here does exactly what we want, and we obtain the index sequence 3, -1, 1 and 1. The dequantization now places the reconstruction values in the center of each cell. This results in a sequence that is close to the original but not identical. As mentioned at the beginning, the mean squared error is commonly used as the distortion metric. Here you can see it applied to that example. Keep in mind that these reconstruction values are then used for the inverse DCT. So how are the resulting values affected? This plot shows in red the sum of cosines of different frequencies with different amplitudes for the original sequence. You can see that it goes through all spatial data values. However, because of the lossy reconstruction of the amplitudes, the result of the reconstructed sequence, here shown in green, misses them slightly. The choice of the thresholds and the reconstruction values of the quantizer directly affect both the rate and the distortion. Of course, those values can be different for different coefficients. In JPEG, for example, the DC coefficient is usually more important to the visual perception than all the other coefficients. Thus, a final representation is desired. It is up to the rate allocation to control those quantization parameters. The objective is to minimize the distortion while not exceeding a certain rate, or, equivalently, to minimize the rate while not exceeding a certain distortion. In JPEG, the 8x8 DCT coefficients of each block are quantized with a uniform quantizer as shown in the quantization example in the previous slide. For each frequency, a different cell width delta is used. Those deltas are scaled by a quality parameter, which affects rate and distortion. The optimal ratio between the quantization parameters of different DCT frequencies has been determined by visual experiments and thus are optimized for visual perception rather than a more formal distortion metric like the mean square error. That is the reason why JPEG usually performs bad MSE-wise compared to other methods, but the perceived quality is pretty good. JPEG 2000 uses a way more sophisticated approach that I will only describe very superficially for now. First, all wavelet coefficients are quantized very finely. Then, for each frequency and blocks of spatially neighboring quantized coefficients, only the most significant bit is encoded, then the second most significant, and so on. Those chunks of data are called bit planes. For each bit plane, the contribution to the rate and to the distortion reduction, if it was included, is measured. Based on that, they are sorted by the quality-rate ratio and written to the final stream in that order until a predefined rate is achieved. This approach guarantees minimal distortion. Of course, this method is only as good as the underlying distortion metric. So far, we've transformed and quantized our image. Let's see how it gets actually written on the disk. Before we can see how we encode information efficiently, I want to give you a feeling of what information actually is. According to Claude Shannon, the founder of information theory, information is that what reduces uncertainty. That means something likely contains less information than something that is surprising to us. We can quantify that by saying that information is the minimal number of yes-no questions that are required to track down information. The given formula describes exactly that, where P stands for the probability of an event of all possible events. Let me clarify that with the following example. Say we are calling a friend and want to ask him what the weather is like at his place with just yes-no questions. For the sake of simplicity, only the 4 mutually exclusive types of weather are valid: sunny, cloudy, rain, and snow. Since no additional information is available, it is reasonable to assume that all possible weather conditions have the same probability, here 25%. This results in the here displayed decision tree. As you can see, for each type of weather, we need to ask exactly 2 questions to track down that information. Let's see how we can formally compute that. For each event, we simply add up the number of yes-no questions we need to ask, weighted by the probability of the event. However, if we can make more accurate assumptions on the probabilities of the individual events, we might be able to do better on average. Let's assume that we know our friend is located in Germany. Then the probabilities are different. Let's say there are 50% for clouds, 25% for rain, 12.5% for sun, and 12.5% for snow. Of course, we would ask the most likely first in order to overall ask fewer questions. As you can see here, on the average, we can expect 1.75 questions for that scenario. Thus, we're able to benefit from our assumption. However, the probabilities are in fact different. Let's say sun is in fact the most likely type of weather. We can easily increase the expected number of required questions when still asking in the same way. But how can that help us with compression? That's what we use the entropy encoder for. Since the energy compaction property of the decorrelation transform results in very small numbers for most coefficients of spatially correlated data like natural images, we can take advantage of that knowledge and use code words that require less bits for small values and more bits for large values. On the average, we can save data with that approach because small numbers are much more likely than large numbers. But what grade can we achieve in the best case? This is given by the Shannon entropy, which is computed by the given formula. In our case, Pi describes the probability of coefficient to be quantized to the quantization index I. Does that formula look familiar to you? Yes, it is the exact same formula that we used to compute the expected number of yes-no questions in the previous example. This formula, however, assumes that the samples are independent from each other. If the decorrelation we put so much effort into did a good job, then this assumption is true. So what code word do we have to assign to which index to minimize the rate? Derived from the above formula, the length of the symbol's binary code word should be the base 2 logarithm of the inverse probability. To be able to decode a sequence of code words, no code word must be the prefix of another code word. For example, say we have both the code words 01 and 011. If the encoded sequence contains 01, the decoder is unable to say if it should decode the code word 01 or read more bits to see if it actually is the code word 011. A very common algorithm to create such code words is the Huffman's algorithm. It is also deployed in JPEG. If all symbols have a negative power of 2 as their probability, the Shannon entropy is reached because all code words have integer length. Thus, Huffman coding is optimal for that case. For other probability distributions, Huffman coding is suboptimal because code words with non-integer length are required to achieve the Shannon entropy. A different approach called arithmetic coding does exactly that. It encodes the entire sequence with one single code word so that on average, fractional length for individual code words are achieved. For an infinite long sequence of independent samples, the Shannon entropy can be achieved for arbitrary probability distributions. Arithmetic coding has proven to achieve excellent performance in JPEG 2000, where it is used to encode the individual bit planes. How arithmetic coding actually works is out of the scope of this presentation. Let me summarize what we've learned today. Lossy data compression is based on two concepts. Number 1, reduction of redundancies. The dependencies between the pixels are removed. The image shall be transformed so that the energy is concentrated in a few coefficients rather than spread amongst the entire image. This decorrelation of data allows us then to efficiently describe the information using entropy encoding. Despite rounding errors, the reduction of redundancies is completely lossless. For most applications, the roughly 50% compression ratio we can achieve by that for natural images is not enough, and a second step is required. This is the reduction of irrelevant information. That means the information shall only be described as accurate as necessary. The distortion shall be kept to a minimum for a given rate. Thereby, it is wise to consider the visual perception, for example to encode chrominance with less accuracy than the luminance. For those of you who want to dig into compression a little deeper, I can recommend you to read the following. Data Compression, the Complete Reference, from David Salomon. Even though the title claims a lot, you won't be disappointed. Salomon gives an excellent overview of virtually all available compression methods and also gives a very intuitive insight about the theory behind them. JPEG, Still Image Compression Standard, which by the way is also known as the Pink Book, contains all details about the JPEG standard. Since it gives only little background information, I can only recommend it as a reference. JPEG 2000, Image Compression Fundamentals, Standards and Practice, gives an excellent overview of the JPEG 2000 standard. It found the right balance between theory and practice, that you will not only be able to understand how JPEG 2000 works, but also why it works. If you're a math guy and really want to know what's going on behind the scenes, Grace and Neuhoff's paper Quantization gives a very detailed overview about rate distortion and information theory. But beware. This condensed work does not contain any real-world applications, examples, or intuitive reasoning whatsoever.